In the last video, we talked about how the cell uses a sodium-potassium pump and ATP to maintain its potential difference between the inside of the cell, or the inside of the neuron, and the outside. And in general, the outside is more positive than the inside. You have a minus 70 millivolt potential difference from the inside to the outside. And it's minus because the outside is more positive, or less positive minus more positive, you're going to get a negative number, and it's by minus 70. Now, I said that this was the foundation for understanding how neurons actually transmit signals. And to understand that, I'll kind of lay a foundation over that foundation. I think then just the actual neuron transmission will make a lot of sense. And even better, it'll make a lot of sense why they even have these myelin sheets and these nodes of Ranvier, and why we have all of these dendrites. Hopefully it'll all fit together. So there are two types of ways that kind of a potential can travel. So there's two types of signal transfer. I'll just call it signal transfer. I don't know what the best word for it is. The first one I'll talk is electrotonic. It sounds very fancy, but you'll see it's a very simple idea. Electrotonic potential. And the other one I'm going to go over is an action potential. And they both have their own positives and negatives in terms of being able to transmit a signal. Action potential. And we're talking about within the context of in a cell or across a cell membrane. So let's understand what these mean. So let me get my membrane of a cell. Let's say it's a nerve cell or neuron, just to make it all fit together in this context. And we know it's more positive on the outside than the inside. We know that there's a lot of sodium on the outside, or a lot more sodium on the outside than on the inside. There might be a little bit. And we know there's a lot more potassium on the inside. There's a lot more potassium on the inside than the outside. But we know generally that the outside is more positive than the inside, because our sodium-potassium pump will pump out 3 sodiums for every 2 potassiums it takes in. Now, in the last video, I told you that there are these things called, well, we could call them a sodium gate, a sodium ion gate, right? These are all ions. They're charged. Now, let's say that there's some reason, some stimulus. Let me label this. This is my, let me scroll down a little bit. This right here, that right there is my sodium ion gate. And it's in its closed position. But let's say something causes it to open. And we'll talk of, maybe in this video, or maybe this video and the next, about the different things that could cause it to open. Maybe it's some type of stimulus causes it to open. Actually, there's a whole bunch of different stimuluses that would cause it to open. But let's say it opens. What's going to happen if it opens? Well, if it opens, so let's say we open it. Some stimulus opens, what's going to happen? We have more positive on the outside than the inside, so positive things want to move in. And this is a sodium gate, so only sodium can go through it. So it's kind of a convoluted protein structure that only sodium can make its way through. And on top of that, we have a lot more sodium on the outside than on the inside. So the diffusion gradient is going to want to make sodium go through it. And the fact that sodium is a positive ion, the outside is more positive, they're going to want to run away from that positive ion, from that positive environment. So if you open this, you're just going to have a lot of sodium ions start to flood through. They're just going to start flooding through. A ton of sodium ions are going to flood through. Now, as that happens, what's going to happen if we go further down the membrane? Let's zoom out. Let's zoom out. So let's say that this is my membrane right there. Let's say that this is my open gate right here. And that it's open for some reason, and a bunch of sodium is flowing in. So all of this is becoming much more positive. Much more positive. Let's say we had a voltmeter. Let's say we had a voltmeter right here, where we're measuring the potential difference between the inside of the membrane and the outside. So let me do a little chart. Let me do a chart. So I'm going to do the chart here, my voltmeter. And on this is going to be the potential difference, or we'll call it the membrane voltage. Membrane voltage, or the voltage difference across the membrane. And let's say this is time. And let's say right now, let's say I haven't opened this gate yet. So it's in its resting state. Our sodium-potassium pumps are working. Things are leaking back and forth, but it's staying at that minus 70 millivolts. So that right there is minus 70 millivolts. Now, as soon as this opens, as soon as this gate that's way down, some other part of the cell opens, what's going to happen? And let's say that's the only thing that's open. So this all of a sudden is going to become more positive. So positive charge that's already here, so other positive charges, whether they're sodiums, let me stick to the same color scheme I've been doing, whether they're sodiums or potassiums, they're going to want to run away from that point because this area hasn't had a flood of positive things, so it's less positive than this over here. So maybe we have some potassiums, and maybe we have some sodiums. Everything is going to want to move away from the place where this is opened. Everything is going to, the charge is going to want to move away. So as soon as this happens, as soon as we open this gate, we're going to have a movement of positive charge in this direction. So all of a sudden, this was, at minus 70 millivolts, some more positive charge is coming its way. So it's immediately, almost immediately, because these charges are going to push on each other, almost immediately it's going to become less negative or more positive. It's the potential difference between this and this is going to become less. So this is at this point over here. Now, if we took this point, if we did the same thing, let me do it in a different color. If we measured the voltage at this point right here, maybe it was at minus 70 millivolts. Maybe a fraction of a minute amount of time later, the positive charge starts affecting it, so it becomes more positive. But the effect is diluted, right? Because these positive charges, they're going to radiate in every direction. So the effect is diluted. So the effect on this thing is going to be less. It's going to become less positive. So in an electrotonic potential, what happens is at one point in the cell, a gate opens, charge starts flooding in, and it starts affecting the potential at other parts of the cell. But the positive of it is it's very fast. It's very fast. So this is fast. Right? As soon as this happens, further down inside, this is the inside of the cell. This is inside. Further down the cell, it starts becoming more and more positive. But the further you go, the effect gets dissipated. So you could say the effect dissipates. Effect dissipates with distance. So if you care about speed, you would want this electrotonic potential. As soon as it happens, it'll start affecting the rest of the cell. But if you wanted this potential change to travel over large distances, for example, let's say if we got all the way to this point of the neuron, and we wanted to measure it, it might not have any impact. Maybe a little bit later, but it's not having any impact because all of this gets diluted by the time it's increasing the charge throughout the cell. So its impact far away from the initial place where the gate opened is going to be a lot less. So it's really not good for operating over distance. Now, let's try to figure out what's going on with an action potential. And you might understand this might involve more action. So let's start off with the same situation. We have a sodium gate. We have a sodium gate that gets opened by some stimulus. But what I'm going to do, let me draw two membranes here. Let me draw, so this is the outside of, this is the outside. This is the inside. And let me draw, maybe we're dealing with and we'll go in more detail. Maybe this is an axon or something. But let's say let's say it looks like that. Let's say we have another sodium gate right here. Let's say we have a sodium gate right here. And then they're alternating essentially. So they're alternating. So then I have another sodium gate. I was going to draw another membrane the other side of the cell, but I think I could just draw them alternating like this. So I have another sodium gate right there. Sodium gate right there, and I don't want to do a bunch of these. I think I just have to draw one round of it for you to get what's going on. And let me draw another potassium gate. Another potassium gate, just like that. All right, and let's say that they all start closed. So they're all in the closed position. Now let's say that this sodium gate gets stimulated. It gets opened. So this guy right here gets, let's say that guy right there gets opened. It gets stimulated by something to get open. We'll talk about the things that stimulate. Well, let's say in particular, this thing gets opened. So let's say that sodium ion gate, open. Let's say the stimulus, it has to be a certain voltage. And let's say they become open when we are at minus 55 millivolts. I'll write the word at minus 55 millivolts. So when we're just in our resting state, the potential difference between the inside of the cell and the outside is minus 70. So it's not going to be open. It's going to be closed. But if for whatever reason this becomes positive enough to get to minus 55 millivolts, all of a sudden this thing will be open. And let's write a couple of other rules that dictate what happens to this gate. Let's say it closes. let's say it closes, and these are all rough numbers, but the main idea is for you to get the general idea. Let's say it closes at, I don't know, plus, let's say it closes at plus, I don't know, 35 millivolts. And let's say that our potassium gate opens. Let's say it opens at plus 40 millivolts, just to give an idea of things. And let's say it closes, potassium gate closes at, oh, I don't know, minus 80 millivolts. So what's going to happen? Let's say that for whatever reason, the voltage here has now become minus 55. Let me do a chart just like I did down here. So I want to have space to draw my chart. So chart just like I had here. Just like I had there. This is membrane voltage. Membrane voltage. And this is time down here. And let's say we're measuring it. Let's say this is the membrane voltage at, let's say, right by the sodium gate right here. So we're measuring this voltage across this right here. So if it's not stimulated in any way, we're just here flatlining at minus 70 millivolts. And let's say some stimulus, for whatever reason, makes this more positive. Maybe it's some type of electrotonic effect that's making it more positive here. Maybe some positive charges are floating by, so this becomes more positive. So let's say this becomes more positive, and then the ATP pumps, the sodium potassium pumps pump it out, so it doesn't get to the threshold of minus 55. So then nothing will happen, right? Didn't get to the threshold. But then let's say there's another electrotonic, or maybe a bunch of them, and there's a lot of positive charge here. So we get to the minus 55. We get to the minus 55 millivolts. Remember, when positive charge comes by, we become less negative. The potential difference becomes less negative. We get to that minus 55 volts. This thing opens then, right? This was closed before. It was closed when we were just at minus 70. So let me write here. So at this point, let me make that arrow nicer. At this point, our sodium gate opens. Now, what's going to happen when our sodium gate opens? When that opens, we've seen this show before, all the positively charged sodium is going to go down there, both electric gradient and diffusion gradient, and they're going to flood into the cell. They're going to flood into the cell. There's so much sodium out there, it's so positive out there, they just want to come in. So as soon as you hit that threshold, even though this might have only gotten us to minus 55 or maybe minus 50, all of a sudden that gate opens, and we have all of this positive charge flooding into the cell, so the potential difference becomes much, much more positive. So it becomes much, much more positive. So they keep flooding in, it becomes much, much more positive. But as it gets more positive, we says it closes at plus 35 millivolts. So let's say, let me clear some of this. Well, actually, I don't want to clear that. Well, let me clear it, just because I want to make this. So let me clear that there, just so I can make my graph nicely. So let's say that we're dealing here. Let's say that this up here is plus 35 millivolts. So here it closes, and at the same time, that stuff I just deleted, I said at plus 40 millivolts. Or let's say at plus 35, just for the sake of argument. Let's say at plus 35 millivolts, our sodium gates open. So what's happened here? All of a sudden, so we're at plus 35 or maybe plus 40 millivolts. So this is plus, let's just say plus 40. I think you get the idea either way. So we'll say plus 40. Plus 40 either way. So at plus 40, this guy's going to close. So this guy shuts down. No more positive ions are coming in. But now we are more positive inside, at least locally, at this point on the membrane, than we are outside. And so this gate will open. So then our sodium gate will open. K plus ion gate opens. Now when that opens, what happens? We have all of these sodium ions here. We already saw from the sodium potassium pump that the potassium, we have all of these potassium ions here. We saw from the sodium potassium pump that it makes the sodium concentration on the outside higher and the potassium concentration on the inside higher. And now that we've gotten to this plus 40 millivolt range, we're also now more positive on the inside. So this opens. These guys want to escape because there's less potassium outside. They want to go down their concentration gradient. And it's also very positive on the inside. We're at plus 40 millivolts. So they also want to escape. So they start escaping the cell. So positive charges starts exiting the cell from the inside to the outside. So we become less positive again. We become less positive. So let me write what happens here. So at this point, our sodium gate closes, and our potassium gate opens. Our potassium gate opens, and then the positive charge starts flooding out of the cell again. Starts flooding out of the cell. And maybe it'll overshoot, because it's only going to close maybe once we get to minus 80 millivolts. So maybe our potassium gate closes at minus 80. So K, let me scroll down. K plus closes, gate closes. And then our sodium potassium pump might get us back to our minus 70 millivolts. So this is what's happening just at this point in the cell, just across, near that first sodium gate. But what's going to happen in general, right? As this became very positive, we went to 40 millivolts over here. We went to 40 millivolts in this area of the cell. Because of, I guess you could almost view it as a short term or a very short distance electrotonic potential, this area is going to become more positive, right? This is going to become more positive. These positive charges are going to go where it's less positive. So this is going to become more positive. This was at minus 70, but it's going to become more positive. It'll go to minus 65, minus 60, minus 55, and then bam, this guy will get triggered again. Then this guy gets opened. Then this guy gets opened, sodium floods in through here. So if you wanted to plot this guy's, the potential difference of what's going on across this, this all happened as soon as, maybe as soon as the sodium started going in this first dude. The second guy, he gets triggered here because at the second guy, a little bit later in time, because of all this flow a little bit to the left of him, his potential goes up. He gets triggered. Same exact thing happens to him, right? When the sodium flows in here, becomes really positive around here, that makes the cell around here, the voltage around here, the charge around here a little bit more positive, triggers this next sodium gate to open. And then this whole same thing happens, same cycle. Then the potassium gates open to make it negative again. But by the time that's happened, it's become positive over here to trigger another sodium gate. So one after another, you have these sodium gates opening and closing, but it's transmitting that information. It's transmitting that potential change. So what's going on here? So this is slower, and it actually involves energy. So the electrotonic was very fast. This is slow. An action potential is slower. I don't want to say it's slow. It's slower because it has to involve these opening and closing of gates. And it also involves energy. It also requires more energy. You have opening and closing of gates, and you're also going to have to keep changing the potential in your cell, and you actively have your sodium potassium pumps being very active. But it's good. The positive is it's good at covering distance. Covering distance. When you have something like this, we saw with electrotonic, as we get further and further away from where the stimulus happened, the change in potential becomes more and more dissipated. It's actually exponentially declines. It becomes more and more dissipated as we get further and further away. So it's not good for long distance. This thing can just continue forever, because every time it stimulates the next gate, it's like we're starting all over again. And so this gate, it's going to have a flood of ions come in. Then those ions are going to make it a little less negative over here. Then the next gate's going to open, and we're going to have the cycle over and over again. So this is really good for traveling long distances. So now we have really the foundation to understand exactly what's happening in a neuron. And I'm going to go over that in the next video to show you how electrotonic potentials and action potentials can combine to have a signal travel through a neuron.